Well, now we're going to be starting Lecture 10, Part 1, and the subject is radar clutter. Radar clutter is a description of the phenomenology of the backscatter from objects that aren't the target of interest. And a lot of the time, when I've looked at the statistics of the people who watch the different sections in the lecture, the radar clutter isn't looked at too much. Not as much as signal processing, tracking, transmitters and receivers. But after 35, 40 years of working in radar systems engineering, it is one of the most important. It may seem dull, but it is extremely important to know the characteristics to detail of radar clutter in order to put together a working radar system. And I'm going to talk about that a fair amount in the first view graphs to point out examples, historical ones, that are just as valid in today's radars as to why radar clutter is extremely important to the performance of radars as a whole. It's literally whether the radar will work or not. Okay, here we have our block diagram of the radar system. And the important thing here is the radar pulses are transmitted out through the antenna. They collect echo data on the target radar on the targets. And down here also we have a picture of some buildings, which are just one example of objects which the radar energy can backscatter off of. And then in the next view graph or two, you'll see a lot of the different objects that, along with the targets of interest, that the radar energy can impinge upon and reflect back. And they will produce deleterious effects throughout this whole chain if not understood and dealt with appropriately with the radar as a matter of things like choosing frequency in some cases. Exactly how the Doppler processing or clutter ejection algorithms are developed. The dynamic range in the A to D converters, the spectral purity of the transmitter and the receiver, and also how the tracking algorithms are developed, and so it's a whole. It impinges on all elements of the radar design, and in many cases in the past I have seen time after time, generation after generation of radar subsystem designers have ignored the effect of clutter on how the design of their part of the radar system would make life very, very difficult, impossible as a matter of fact, for other parts of the radar. And so this emphasizes over and over again that the whole radar design process should be interactive and synergistic between all the subsystems. And one of those particularly that's terribly important is a thorough knowledge of radar clutter. Okay, now let's look at the overall lectures on clutter. There are actually about 120 view graphs, so I broke it up into two parts. Something of that order of magnitude. We're going to be studying the motivation as to why, because there's a lot of data for you to see, and I want to put through examples as I show you numbers and trends on different kinds of backscatter from unwanted objects, why they're important to the performance of the radar. Again and again, and not just have you look at the individual words on numbers associated with different backscatter properties at different frequencies on the ground, the sea, the rain, and birds and insects and what have you. So first, let's move on to motivation. So the question is, why study radar clutter? And I've been talking about that with you. And this just points out that in a naval air defense scenario, you've got not just the targets of interest, here a couple of fighters and here a cruise missile, but you've got backscatter from the ground and urban objects, hills nearby, flat lands. You've got the sea, bird flocks, rain. It may be unwanted, unnatural objects, chaff, which are in most cases dipole, dropped from an airplane. More birds over land. They might be migrating. They can be at altitudes as high as 17,000 feet in some cases when they're migrating from one continental area to the other. And when they're doing that, they're in flocks, so they're very complex targets. And when we talk about ground clutter, which we will, there's an awful lot of different kinds of ground physically that you can backscatter off of. Urban, it could be farmland, forested areas, marshy areas, built-up cities, suburban areas, deserts, very high mountains. So there's all kinds of different kinds of ground clutter. And this is just an overview of all the different kinds of clutter that there are and how they can just see, wow, there's a lot. There's a curse, not just in the characteristics of these different kinds of clutter, but in how they do their thing. Whereas a single isolated large seagull is a single target, and it is a target, and it's a point target, relatively speaking. Then you've got rain that's diffuse and moving with the wind speed. Now here I wrote down a couple of big picture, for me, probably the 4 biggest reasons that you really want to understand clutter. You're going to try to get rid of this clutter with Doppler processing, and we're going to spend a considerable amount of time, many lectures, looking at how to suppress the clutter. Now, if we don't suppress it below the noise, there's some residue of the clutter backscatter that's above the noise levels in your receiver. If you don't have enough dynamic range, you don't have bits in your A to D converter, that sort of thing. And for ground, rain, and sea clutter residue, they can tend to be correlated in time and in space. And so they will give special problems to trackers which inevitably are based on the fact that the clutter background is random. The background is a random noise. But if they're correlated in time and space, the trackers can just fall apart, and you get lots of tracks from ground, rain, and sea that are correlated. And birds are real targets. They can overload trackers, and you'll see later when we look at their size relative to many targets, even in the unclassified world, the distribution of the cross-section of birds is greater than the distribution. It overlaps the distribution of aircraft in a commercial, a benign U.S. environment. There are a lot of single-engine pleasure aircraft, single-seaters, Cessnas, Piper Cherokees, and you look at them nose on, and a lot of birds in flight have larger cross-sections. And especially during migration, the densities can be overwhelming, and we'll show you examples of that. And we're also going to be talking about range and Doppler ambiguities. That is, that a characteristic of sampling in the frequency domain to do the Doppler processing digitally gives rise to Doppler ambiguities, which means that 150-mile-an-hour target can be in the same Doppler cell as a 250 mile or a 50 mile an hour. They can fold over depending upon the pulse repetition interval and the things and the frequencies, things like that. And you can have range ambiguities where a faraway mountain range can give you a detection that appears to be from the last pulse you sent out, but it's from the one before it. So second time around range ambiguity problems can complicate these issues. These are quick sentences which I'll be going over in much more detail, but they complicate greatly, and what they say is the range Doppler velocity space gets scrunched down so that fast-moving objects can be in the same Doppler domain as slower-moving objects, and slower-moving objects can be point clutter like bird migrations and things like that. And in addition to that, many different targets these days, you know, there's the push. Everyone in the military wants to make their targets very, very, very small. And that says that birds, if they can be seen by single-engine Piper Cherokees, they're the same order of magnitude. When you make them very, very small, birds are going to be a significant false target issue. And that again will say that the radar design needs to be holistic and taking into account all these different and more different coinciding constraints when you design the radar. Now I'm going to be saying again and again, talking about the most important factor that's important in Doppler processing, and that's your ability to improve your processing in clutter. And that's called the MTI Improvement Factor. And that is defined as the MTI Improvement Factor I as a function of Doppler is equal to the signal to the clutter ratio out of the processor divided by the signal to clutter ratio which goes into the processor, and that's measured at a specific Doppler frequency. So there are certain Doppler frequencies, and remember, the Doppler frequency corresponds to your radial velocity of a target. So there's certain Doppler frequency where you may have very good signal-to-noise ratio, and certain Doppler frequencies you may have very poor. And it might be reasonable on average, but that area that you have poor Doppler, a poor MTI improvement factor, those Doppler frequencies can give very poor performance overall. Here's just a relative power as a function of radial velocity for a number of different, just to give you the relative size. Land clutter typically can be up in relative power, let's see, 55 dB rain and the 30 dB lower than that, and an aircraft in this region. But it can go down to levels you can't find out about. And so it's a real problem to suppress the land clutter, the rain clutter, the sea clutter also, and to deal with the bird issue when the aircraft are typically smaller than they are. And another way of looking at this MTI improvement factor is that the MTI improvement factor is the clutter attenuation. That's the ratio of the clutter power in to the clutter power out times the signal gain, the signal out divided by the signal in. Now, radars for which clutter is an issue, and here are just a large number of them. Some airborne radars that are used for surveillance and tracking, the Hawkeye E2C, and the AWACS E3A, the over-the-horizon radars that will look over the horizon at frequencies between 3 and 30 megahertz. Air surveillance radars, this one on a carrier, a parabolic one. Also, the SPS-48, which we looked at that when we were studying antennas, and the phased array radars on the Aegis. In this case, it's an Aegis cruiser, and the Spy-1 series, and they will have certainly sea clutter. And just to look at more, the Joint Stars radar, which looks down at ground moving targets on the ground. Well, if it's looking at the ground for moving targets, clearly, to help out with the drug interdiction program, there's a radar under this aerostat, which looks down towards the ocean to look at small boats or aircraft in the Caribbean and other places. The FAA's en route surveillance radars, this one, the ARSR-4, which does long-range surveillance and tracking, looks for aircraft at all altitudes up that aircraft operate to commercially. A Wedgetail, an airborne radar that is built for Australia. Now, the ways to handle noise and clutter are really two. One is if you've got noise and you want to deal with it, you can crank up the power. And if you want to do signal processing to get rid of the clutter, you've got to do very sophisticated signal processing. And this is a little photograph of another colleague of mine at Lincoln Laboratory, Steve Weiner, and myself. And I always love now to look at this photograph. I've lost about 50 pounds since it was taken a number of years ago. And so you really have to use finesse. There's a number of different reasons why finesse is needed in signal processing and power is needed in noise. And the reason is because it's much more complicated to do the signal processing than to just add brunt force power. But getting up these days, some of the more very sophisticated signal processing algorithms need the power of digital special purpose computers to do those very complicated algorithmic processing techniques that allow us to suppress the clutter. And I added this little set of thoughts of both of us while we were having fun taking the picture. It was mutually agreed upon as to what we do. Anyway, in the next couple of view graphs, we're going to be looking at a typical air surveillance radar that's used at hundreds of airports in the United States. And here's a picture of one in the Boston area. I believe it's an ASR 9. It might be an 8. But they all have basically the same parameters. They operate at S-band, 10 centimeters wavelength. They're and the frequencies are 2700 to 2900 megahertz. They have an instrumented range to 60 nautical miles, peak power of about 1.4 megawatts, and average power less than a kilowatt. And the repetition of pulse repetition rate, the PRF, averages about a kilohertz. The antenna rotates at 12.8 RPM. This part down here is the radar antenna, and this section up above is a beacon antenna that does identification of the aircraft cooperatively, and sends out a pulse, interrogate a pulse, and then the aircraft sends back a message yes, I'm that aircraft you wanted to speak to, and it sends back its identification and its altitude. So these radar systems get out not only through a non-cooperative so-called skin track, the radar data, but also cooperatively the altitude of the aircraft and its identification, which is greatly helpful to the air traffic controllers in doing their air traffic control function. The size of the ASR 9's antenna is about 4.8 meters by 2.7 meters, and the gain's about 33 dB. I believe this is actually an ASR 8.